Okay, so we will go ahead and get started with our final plenary talk of this week's workshop. So Marina Meila will talk to us about Manifold Learning 2.0.
Hello again, and it's a pleasure to be here, even if virtually. I'm aware that this is the last talk of the day, so I will try not to put much pressure and not to keep you past the weekend and maybe the party that follows. This is work. This is more recent work that builds on on my older work on manifold learning, and it is done in collaboration with my students Yucha Chen, Samson Cole, and Hanyu Zhang, and my collaborator from Johns Hopkins University, Ioannis Kevrekidis. So the motivation from this work comes from the need to place manifold learning in a closer context to mathematics and the sciences. And mathematics and sciences have developed over the centuries a close symbiosis in which now machine learning steps in, and machine learning does communicate with the sciences and is used in the sciences, but it's mostly used by means of the data. And so machine learning is great to model one data source. However, there has been little success and actually not so many attempts to make machine learning actually communicate the science in terms not of just data and models of a single data source, but in terms of higher level scientific concepts. So the talk today is going to try to bring manifold learning closer both to the sciences by actually making the output of manifold learning interpretable in scientific terms, and closer to mathematics, because mathematics is manifolds are so support so much other rich mathematics, and so if we are able to learn manifolds, maybe we can learn other concepts like vector fields on manifolds, and if we are able to learn and estimate the Laplace-Beltrami operator on a manifold, maybe we can also estimate higher order Laplacians. So this is the second part of the talk that I'm going to give. So in the first part, I'm going to formulate the interpretability of the output of manifold learning in a particular formal sense, and I'm going to show how this problem can be solved in that sense. In the second part, I'm going to talk about estimating the first order Laplacian and using it for deriving various results in manifold analysis, both topological and geometric. So, as I said, the first part, we want to actually interpret the manifold learning, the output, the manifold that was learned from data in terms of the science that underlies this data. And here is an example. In the study of molecules, one does very expensive and very rich simulations, very detailed simulation of the configuration space of molecules. And of course, these are interesting for large molecules like proteins. Here, I'm going to exemplify the work with small molecules, which are actually completely understood or well understood by scientists, but they're still interesting by exemplifying what we want to do for larger proteins, larger molecules. So this molecule ethanol has 9 atoms, and these atoms look like as if they're in first approximation look like an articulated toy, but in reality they vibrate in space. So this molecule has around around 20 dimensions. So this is like approximately 20-dimensional space. And so if we represent these configurations in 2 of these multi-dimensional configuration spaces, we see something that's like a triangle. Yeah. Now, this molecule is actually very simple. And so if we have some very simple pre-processing that involves essentially some procrustes and PCA, we see that in fact, this configuration space is a noisy torus. Yeah, one of the generators of the torus is very visible, the other one is much smaller, and it's hidden here in the noise. So perhaps if we don't do smoothing and manifold learning, we are not going to see it. Yes. And this noisy torus could be learned by manifold learning. If you were in the lecture this morning, you can see that manifold learning does smooth the data. So the torus is clearly visible. But it also distorts the data, and we have talked about this morning about why this happens. I actually on purpose left this distortion to be quite visible because this is part of the game. We have to be aware, and whatever we do with the results of manifold learning, we have to be aware that there is a distortion to handle. Yeah. Now, for this audience, it's probably very obvious why this is a torus. It's a torus because in first approximation, these two parts of the molecule rotate with respect to the middle part, and this produces the two generators of the torus. In particular, this rotor produces the larger generator, and this rotation produces the other generator. Yeah. Okay. If we are a scientist, a chemist will already know this, and so they will ask a graduate student to plot these torsions, the yellow torsion and the purple torsion that's less visible here, on the embedding of the data, and that will confirm the hypothesis that the yellow torsion is responsible for this generator and the purple for this other generator. Yeah. So we have done manifold learning, and then we gave the results to the scientists who used their knowledge to try various torsions or use their intuition to actually show that these torsions are something that is natural and describes at a higher level the behavior of the molecule. Okay, but now for a larger molecule, you can imagine that one would have to plot many more torsions to find the right one, or the right two, and this task can become quite tedious to do manually. And graduate students are still highly trained people. This can't be crowdsourced. So we would like to actually help the scientists, but by discovering these features automatically. Yeah, and the rest of the talk will be about this: how to use the prior knowledge of the scientist to discover something about the manifold learning, the learned manifold. Yeah. To make it even clearer, we have data, we have the molecule, and we have data from these configurations from which we build some representation, a lower dimensional representation. Now, this lower dimensional representation is in some embedding space that is sort of abstract. The coordinates have no meaning. Just like when we do principal component analysis, we map the space we map the data in a space that has meaning mathematically or statistically, but doesn't have a physical meaning yet. Yeah, and that's what I mean by abstract. They're well defined mathematically by the algorithm, but they're not defined in terms of the science. Okay, so the science, though, the scientists can introduce their scientific language and say, hey, it's not the coordinates that matter, it's the torsions. And in that case, we can formulate our problem as saying, give me a dictionary of all torsions that could be conceivably represent coordinates for this abstract manifold. Give me a manifold learning algorithm that produces an embedding for this manifold. And then our algorithm is going to take the dictionary and take the embedding and put them together and find in the dictionary another set of coordinates that are just as good for this manifold. Yeah, so the scientist just expresses their knowledge by saying, here are all the possible scientific functions that are of interest to us. And in this case, they're all torsions, but they don't have to be that way. They could be something like pressure, temperature, whatever, and other scientific quantities, age for galaxies, chemical compositions for materials, and so on. Yeah. So the scientist just gives us the list, a list that can be large, exhaustive, of all the functions that are of interest to them and that they hypothesize as describing the manifold. And from data, we derive the manifold, and then our goal is to find in this dictionary some functions that could be coordinates. So find actually a change of coordinates. Yeah. Why is this good? Because we think that for science, science already has a language, and if we want to do machine learning for the sciences, we should output the results in the language of the scientist and not in the language of neurons and activations or other languages that are abstract and not related to the scientist. Okay, let me see if there are questions about the framework or the paradigm. Does this make sense? So in slightly more formal terms, the domain knowledge comes as a list of functions defined in the ambient space, RD, where the data lie, but they could be also just function on the data of the manifold, on the manifold. Yeah. And this, for example, could be all the possible torsions in this molecule. And we also have data, which is in some high-dimensional ambient space. And we have an embedding of the data, which we denote by phi, which is a mapping to a lower dimensional space, which is represented by this learned manifold. Okay, and now we are assuming that the coordinates of this manifold can be represented in terms of some subset of functions from the dictionary. Yeah, so we assume that we can represent this manifold by these coordinates if we knew which ones they were. And what we would like is to find this subset in the large dictionary that we started. Yeah. So this is a sparse regression, right? We want to regress the manifold coordinates. We want to regress the manifold coordinates on functions in the dictionary, and we want to extract a small subset. In fact, the size of the subset is equal to the intrinsic dimension of the dictionary under certain conditions. Yeah. The only problem is that this regression is not linear regression; it's non-linear. Yeah. So it's a regression in function spaces, and H is not a matrix of coefficient, but it's an unknown function. Okay. Moreover, we can't play the usual tricks to handle this unknown function H. Why? Because these coordinates phi are known only up to diffeomorphism. Like this is the definition of coordinates in a manifold. Any nonlinear transformation of phi is also a good set of coordinates. Yeah, and that means that any nonlinear transformation of H should be another H. Okay, therefore we can't choose a basis for H. There is no basis that is natural for H. Yeah, and this can be thought of as follows. If we use a different embedding algorithm, we're going to get a different phi, perhaps. And so that will completely change the basis. Okay. Then we also can't assume the correspondence between the functions in G and the coordinates that we have, because again, that's not guaranteed by manifold learning. The coordinates can mix in any way they want. And moreover, we don't assume that the embedding is isometric. So we don't have isometry either. But that's good because we are not assuming that the G's can embed the manifold isometrically either. And so let's pause for a moment and just think what can be done. So we have a set of functions. We believe that they can be regressed as function of a subset of some large set of functions, but the link function is nonlinear and non-parametric. We don't know what it is, except we know that it's smooth. We can make smoothness assumptions on it. And the answer is fairly simple. We can transform this into a linear problem. And the transformation is essentially Leibniz rule. If function composition, so composition in function space, becomes a linear composition in differential space. Yeah. So the Jacobian of phi is a linear function of the Jacobian of these functions that are the other set of the hypothetical other set of coordinates. And DH is just some linear change of coordinates. Yeah. So now we have transformed a sparse nonlinear regression problem of which we had no idea how to solve into a sparse linear regression, which is something that is very well studied, as all of you know by now. However, this linear regression has some particularities. In particular, this relationship holds gives us for every data point I a linear system where yi are the gradients of the, or the differentials of pi I, x are the gradients of the functions on which we want to regress, and the differential of h is given by these coefficients beta ij. Yes. However, the coefficients change at every point. They depend on the data point because we are in a non-parametric, nonlinear world. Yes. So we have a linear system of equations for every data point, a different linear system of equations. Yeah. So is this hopeless? It's actually not hopeless because we have a constraint, and the constraint is that the subset, the support is the same for all the data points. So even though we can't hope to recover beta with accuracy, but we can recover the support with accuracy by pulling the information from several data points on the manifold. So in fact, we are going to take a subsample of the data on the manifold after the manifold was estimated, and solve a system, simultaneously these linear systems in terms of least squares with the constraints that the support is the same. And if we set the problem in this way, the answer is something that is actually known. It's an optimization problem called group lasso. And the group lasso appears here because we would like the same g, the same functions g to appear in every regression. And so we have a groups of coefficients that should be 0 or non-zero simultaneously. Yeah. And so if you're familiar with lasso and with sparse regression, you are going to recognize this equation. This part is the least squared part. So for every data point I, we want to minimize the least squares, the square residuals. And this part is the regularization part with the norm for, and beta j is the vector of coefficients for one of the functions in the dictionary. Now is a good time for questions. So to repeat, our goal is to find what functions in the dictionary could be coordinates for the estimated manifold. And I do that by setting up a sparse regression problem in which the gradients of the functions in the dictionary are used to reconstruct the gradients of the coordinates at every point. And this is a penalized regression which encourages sparsity. There is a lambda, a regularization coefficient. And so what we're going to get here is a regularization path. The method to set lambda, or the lambda is chosen by selecting the number of non-zero coefficients. So there are, one can prove that under certain regularity conditions, the support of these functions, the size of the support should be equal to the intrinsic dimension. Yes, it's a d-dimensional manifold. The intrinsic dimension is little d. We want d coordinate functions that are independent, and so we need d non-zero coefficients. So what we do, and this will be exemplified shortly. In fact, let me show it now. It's too far. Okay, so what we do is the following. What we do is the following. We construct the whole regularization path. This regularization path is done by binary search. And then we choose the lambda for which exactly two coefficients are non-zero. Yes? And in this case, these two coefficients that are non-zero are the coefficients corresponding to the purple and the blue coordinates, whereas all the others go to 0 before. And the blue happens to correspond to the small circle, the small generator, the vertical one, and the purple one gives two coordinates that correspond to the circular, to the other generator. You noticed here that if we embed in 3 dimensions, we are going phi, the manifold embedding will have three coordinates. However, the generators that we use are circular coordinates. The torsions are circular coordinates, and for circular coordinates, 2 coordinates are sufficient. Yeah, we see also a case where there is a one-to-one correspondence between, or there is a correspondence between the functions in the dictionary and the subsets of coordinates in the other embedding. But this is just happens for this case. It's not general. Okay. So this is the algorithm at work. Let's see now what is the algorithm. And it's in some sense fairly simple. Given the data, given an embedding of the data and a dictionary of functions like torsions, we start by estimating the tangent subspace, and we do this by weighted PCA, which is a standard algorithm for estimating tangent subspaces. And that's because gradients live in the tangent subspace. So we need it to actually place the gradients there. Then we obtain the gradients of the dictionary functions. And these are the gradients in ambient space. By projecting them on the tangent subspace, we obtain the manifold gradients of these functions. Then there is a step that I did not describe at all, and please ask me if you have questions, if you are interested in it. We have to estimate the gradients of the coordinates. Now, manifold learning gives us the coordinates to points, so we have to do something here, and this is a form of pullback to estimate the gradients of the coordinates. There could be many methods, and the one that we chose is more natural in terms of manifold learning. It's not the simplest and the most obvious one, which is just taking differences. It's something more subtle, but it's also more robust, we believe. And now that we have all the x's and all the y's, the last step is just to actually call group lasso. The dimension D is the size of the support that we want, and the output of the group lasso will be the support. It will be just a set of dictionary functions. Yeah. Notice that I haven't been explicit here, but we need much more data to estimate the manifold than we need to estimate the support. So these one to n for the data points can be reduced to a subset of the data that we have. So in our experiments, for instance, we have about 10,000 points for. So in this experiment, for instance, we had 10,000 points to estimate the manifold, but only 100 to estimate the support. Yeah. So every group had size 100. So let's see briefly some theoretical results. There are two kinds of questions that we can ask. When does this work in function space? And then when does it work in a finite sample? And in function space, I'm giving a sketch of a theorem. This works, or works meaning when do we have unique recovery? And to have unique recovery, it means that the coordinates that we choose have to be the only set that can represent the manifold, which means that we can't represent these coordinates in terms of other coordinates also in the dictionary. And this is actually a form of the implicit function theorem. If you have questions about why is this actually not trivial, please come back. Please ask me at the end of the talk. Okay. Then we have results of the kind, when can the group lasso recover the support, again, assuming that the support is unique. And for this one, we derived recovery conditions that are depending on incoherence quantities that are actually very similar to other group lasso proofs. Yeah. What is not similar to other group lasso proofs is that we can't assume that the columns of the vectors x are unitary. And I can explain why. So our incoherence quantities depend on actually on the length, are meant to work with columns of x which are like of arbitrary norm. Yes, and we can derive a very simple recovery conditions in this case. We also have more complex conditions that are basically statistical and assume a sampling error, but I'm going to skip about it. And are more detailed than what I presented, so feel free to ask questions about it. Okay. Now I want to present a little bit about the performance of the method. So this looks well in theory, but how does it work in practice? And we tested this the manifold lasso on synthetic data set. Swiss roll was obligatory to publish the paper, and a rigid molecule that behaved like one of the molecules in our experiments. And then we tested it on real molecules, and we have more tests, more experiments than the ones we show here, in which we had large data sets to estimate the manifold, so the coordinates. We had dimensions that are like moderately large, 50, and in which we used about 100 of the random sample data points for estimating the support, the group lasso. So for group lasso, we had 100 linear systems, whereas for estimating the manifold, we had much more data. What is interesting is the size of the dictionary that I denote by P. We had small dictionaries when we choose 2 out of 12 or 2 out of 30 for toluene, which is a larger molecule, but is simpler. But we also used extensive dictionary that take all the possible torsions in the molecule. And even in molecules that are simple like ethanol and malonaldehyde, the number of possible torsions is combinatorially large. It actually grows like n to the 4th, number of atoms to the 4th. And so the last examples are group lasso with dictionaries of size in the hundreds. Okay, now if you are familiar with group lasso, you know that the amount of regularization that is needed to select 2 out of this large amount of functions in the dictionary is prohibitive, and group lasso may not work so well in that situation. So in this case, we kind of were inspired by other works of people who handled the problem before, and did a 2-stage group lasso in which we first regularized out most of the functions and then continued with basically brute force search on the sets that are left. And this is represented here. These are regularization paths for the very large dictionary, 750 functions in the dictionary. And what we did something very simple. We chose the lambda at the middle of the regularization path, and at this point, most of the 750 functions were gone. And then we did just brute force search on the subset of this, on the subset of the functions that left. And this was actually very successful and always found good coordinates for these 2 molecules. Let me see if there are questions.
Could you say something about the computational time in this case, where you have such large dictionaries, like how?
We implemented our own ADMM group lasso function, and that actually helped. It was much faster than any self-implemented. However, so the dictionary is large. However, we did 2 things to make it faster. First of all, we had only 100 points. So this is multiplied with 100 to get like the size of the matrices, and with the number of dimensions, which is 3. And we also did binary search. So basically, once we found, so the point where all the coefficients are 0 is null. So we didn't have to do regularization for that. And so what we did was very simple. We just calculated the midpoint and did a single group lasso here in this situation. Yes. So we didn't actually follow the regularization, but we did only a group lasso here and selected a small subset. And this subset was, you can see for ethanol is about 20, and for malonaldehyde is much smaller, it's like 12. And then we basically did brute force search for like pairs of these coordinates, which was actually not prohibitive. My student was doing it on his laptop.
Thanks.
Thank you. Are there other questions? This is another like empirical demonstration that we could do this on other molecules. And even though this is actually very noisy, the noise here is not negligible at all. The noise is high, the sampling density is very variable. The noise is multi-scale. However, I must say, fortunately, recovery of the coordinates went well for these molecules, kind of uniformly. Okay, so in summary, technically, we formulated a problem for doing a sparse regression in function space. I haven't shown it, but we have a method for actually getting the gradients of the coordinates of the manifold coordinates back in the ambient space. And we put these 2 together to actually find the support of an estimated manifold in a dictionary specified by the scientist. So what does this achieve from the point of view of the scientist? Now the scientist can use their knowledge in a way that's natural instead of tedious. They can specify what they're looking for, and the algorithm is going to do the looking. And the algorithm is not sensitive to, doesn't need to visualize things, so it can look in higher than 2 dimensions. It can look for complicated manifolds because like everything that can be messed up in visualization is not disrupting the algorithm. It can handle many more functions, many more complex dependencies than a human can do. But more importantly, what is output by the algorithm is important, because now this is transmissible knowledge. And what I mean by this is that if somebody else run an experiment with the same molecule, but in different experimental conditions, as you probably know, they're also going to get a torus. And so just knowing that 2 scientists in 2 different experiments got a torus doesn't mean that they found the same torus. So how do we know that it's the same torus? This method actually allows us to know that it's the same torus because it's explained by the same scientific coordinates. Or if it's not, it's because it's explained by different scientific variables with scientific meaning. And I think this is the importance of what we are doing. That now scientists can communicate knowledge about their manifolds in the language of their domain, which was not possible before. Okay, I want to also stretch that in the dictionary, we don't need to, so the functions in the dictionary are naturally functional independent. Yes, so we can, if the function that is of interest is the log temperature, which is actually common for many physical systems, and we actually input just temperature in the dictionary or 1 over temperature in the dictionary, these are the same function from the point of view of being coordinates, as long as they are 1-to-1 and the transformation is kind of well conditioned. The 1-to-1 transformation is well conditioned. So we don't need to ever put x and x squared and x cubed in the same dictionary. We can put only 1 variable, and all the transformations of those variables will be taken care of non-parametrically. A good time to questions, because I'm about to start on the second part of this research. So now we are changing gears and trying to see if we can learn more mathematical concepts than just manifolds and scalar functions on manifolds. And this is a summary of various things that my group has worked on, from older ones to the newest. The interest now is in vector fields on manifolds instead of scalar functions. And just like the Laplace-Beltrami operator was important for representing and manipulating and analyzing scalar functions, for vector fields, it's the first order Laplacian, which I'm going to sometimes call the Helmholtzian, which is important as an operator. So the first thing we are going to do is to try to find an estimator for the first order Laplacian. Yes, this is an operator on function on vector fields, and so on a graph discretization of the manifold is going to be operate on flows over the edges of the graph. So it's going to be a matrix of the dimension of the edge set of the graph and not of the node set. Once we estimate this Laplacian, its eigendecomposition is called the Helmholtz-Hodge decomposition. So I'm going to explain why this is important. It classifies the vector field on a manifold. And finally, as an application to this, we are going to do something that is the analog of spectral clustering, but in the higher order topology. Or the higher dimensional topology. So instead of giving us connected components, it's going to give us independent loops on a manifold. And representatives that are short representative loops. So let's start. Let's remember first that we assume that there is a manifold, and this manifold has a Laplace-Beltrami operator or some other Laplacian operator. But in reality, you observe only data, and we estimate the Laplacian. And the seminal paper of Koopman and Lafon showed how to estimate the Laplacian in a consistent way, independent of the sampling density. And in machine learning, the estimator of the Laplace-Beltrami operator, L0, was used to embed the data by diffusion maps, to do spectral clustering, to do various smoothing and regularization and representation of functions on the manifold. So we believe that higher order Laplacians that I'm going to define also capture geometry of topology of manifolds, and we would like to estimate the first order Laplacian in order to take advantage of its properties, just like for the zeroth order Laplacian. And this is what we are going to do first. And then we're going to exploit this in smoothing vector fields, embedding graph edges, manifold prime decomposition, which is a bit like spectral clustering, and finding short loop basis, which is also finding representative of these clusters. And these are clusters in terms of edges, not in terms of points. There is little time, so I'm going to pick and choose from these topics. But all this can be done once we estimate the first order Laplacian. Okay, so in a picture, how is the first order Laplacian estimated? Again, there is a manifold that we assume. There are data sampled from the manifold. And then we analyze the data as usual by finding neighbors of each data point. We connect these neighbors by edges, so the red are the edges that we obtain. But then we don't stop there. We also construct triangles. So when three edges form a triangle, we include this in our list and form a list of triangles in the data. And this construction of vertices, edges, and triangles is a simplicial complex of dimension 2, and it's known more or less rigorously as the Vietoris-Rips complex. In practice, most people, when they implement, use what's called the clique complex of this graph. Yeah. Okay. And now, if you're familiar with simplicial complexes, there is a definition of higher order Laplacians on simplicial complexes. And that's by means of the boundary operators, which are actually the incidence matrices of the first and second order. Yeah. So these B's represent the relationship between edges and triangles, and the BE and the BT. Sorry, the BE represents the incidence, the relationship between nodes and edges, and the BE represents the relationship between triangles and edges. Yeah, and W's are just some weights. And any first order Laplacian, actually any Laplacian that's higher order than 0, has two components, a down component and the up component. In our case, the first order Laplacian, which is an operator on edges, has the down component, which depends on the relationship between edges and nodes, and the up component that depends on the relationship between edges and triangles. This part is much easier to derive because it's very related. The relationship between edges and nodes is already captured by the zeroth order Laplacian. So this is just a rewriting, so to say, of the zeroth order Laplacian, and we can derive its properties easily. However, this part is difficult and it hasn't tackled by anyone before. What the main challenge in this part is to find a weight function for the triangles. The reason we want weights, I think I don't have to explain it very much, is that because the correct choice of weights, without the correct choice of weights, we can't prove the convergence of these Laplacians in the limit of the data. And we want to not just prove convergence of the existence of a limit, we want to prove that the limit is actually the manifold operator in the end. Yeah. And we did make a choice of weights for which we could prove convergence of the up and down Laplacian. However, we did not prove complete consistency. We proved consistency up to multiplication of the function. Yeah. So the Laplacian that we have is not provably consistent. Interestingly, when we use it in practice, we did not see where the errors were. And I want to say this not as a boasting, I want to say this as a cautionary tale, where even that in the sense that it is very hard without proofs to actually be sure that our algorithms work. So our algorithms look good and they work, you see, better than the competition. However, this estimation is not complete. There is some bias that needs to be removed still from the estimation. So how does our estimator work in practice? And what else is there? So in red is in this curve in red represents the spectrum of an first order Laplacian estimated by our method. In green, it's a graph Laplacian that's unweighted. So this is like the naive graph Laplacian. And as you can see, I don't know if you can see, but only the red curve has 2 eigenvalues equal to 0. And this is important because this molecule produces a torus. We've seen it before. And so we need to have 2, this means it has 2 cycles, so we need to have 2 zero eigenvalues for this first order Laplacian. And the third method in the middle is a method that is extremely elegant. It's actually also new. Almost similar. I think this is my mistake. I think this is 2018. Yeah, it's a method it's a very elegant method to derive the eigenfunctions of a higher order Laplacian. It's called spectral exterior calculus. However, what is not known is how many. This is the method that's true asymptotically for if we have all the eigenfunction bases. And so in numerical experiments, it doesn't perform as well, although I think it's a much more elegant method than our estimation method. Yeah, and so it's only our estimator that finds the fact that the topology of first order topology of this manifold, the first Betti number is 2. The others only find the Betti number of 1. This is actually this persistent homology little graph confirms that actually the data, the noisy data that we use also exhibits the same topology that we hypothesize. And here are the first 2 eigenfunctions. And remember, these are flows on edges. That's why they look so hairy. They're not functions on the nodes, but on the edges of the graph. Okay, so this demonstrates that the algorithm works, at least empirically. Now, what can we do with it? We are going to do, I'm going to show a few quick things about the analysis of vector fields in pictures, and then I'm going to go to something that is the decomposition of the null space of the first order Laplacian, which is the first cohomology space. Yes, and this has dimension equal to the number of loops beta 1, the first Betti number. But first, let me remind you that the eigenfunctions of the Laplacian represent the basis for the vector fields on a manifold. And even though this is trivial, the interesting thing is that every eigenfunction can be classified as one of these 3 classes. These are the gradient vector fields. These are the curl vector fields, and the null space of the Laplacian is the harmonic vector fields. And the dimension of this space is the number of independent loops on the manifold. For instance, the torus will have 2. So here we demonstrate in practice on another real data set how we can what this bases look like. This real data set consists of buoys in the North Pacific Ocean, because in the North Pacific Ocean, all the islands are very small. There are no loops, so the harmonic space has dimension 0. But we have gradient fields, which are represented here, and curl fields, which are represented here. And we can know for each of them whether it's curl or gradient, because we know which part of the Laplacian it is 0 on. Yeah, and notice that this data, even though this is a vector field on the manifold, what we use from this data are just the points. Yeah, so this is the geometric characterization of the manifold itself and not of the flow that we observe. I'll show the flow later and results with the flow later. So this is just an illustration that we can actually perform the Helmholtz decomposition on real data. Now we can also use the Laplacian and its basis to smooth vector fields. And the smoothing is basically a projection on the lowest eigenfunctions. And if we do that for the ocean data, and the amount of smoothing varies from small to large, we get various smoothed vector fields, this one in the middle being actually the more appropriate and the more accurately representing the currents in the ocean. Another thing that people like to do, and these are just examples of what one can do, and one can multiply these examples as much as we want, so this will be the last, is semi-supervised learning. So in semi-supervised learning, we have the manifold and the graph, but there is a flow on the manifold, and of this flow, we only observe a subset of the edges. Yes, and the horizontal axis in every panel here represents the proportion of edges observed versus the edges unobserved. And the task is actually to predict the flow on the unobserved edges. So as we go from smaller training set to larger training set and smaller test set, the accuracy should always grow. Yes, like here. However, some algorithms perform better than others. And without further ado, I'm going to explain that the first two are our algorithms, and these are always the ones that are the highest. The next two are ridge regression in two versions. One of them is with SEC, and one of them is just ridge regression with our eigenfunctions. And the last one is actually the unweighted, the naive version. If we don't use weights, what will happen? And the last one is actually very often underperformed. Okay, so I have demonstrated just a few examples of the variety of things that we can do in the analysis and learning of vector fields if we have the Helmholtz decomposition and the lowest principal eigenfunctions of the first Laplacian. Now for the last 5 minutes probably, I am going to look at specifically the harmonic embedding. So the harmonic embedding, to remind you, represents the mapping of the edges of a graph with respect to the harmonic vector eigenfunctions or eigenvectors of this graph. Yeah. Why do we care about it? Because this is related, or we hope it would be related to something called prime manifold decomposition. And that is the opposite of the connected sum. So in a connected sum of two manifolds are glued in such a way that the individual topology is preserved. So no new, the dimension of the homology spaces is preserved at all dimensions. Yeah. And now our interest in the data analysis and machine learning is, if we are giving a composite manifold, can we decompose it into its component parts? So it's a form of clustering, but in a topological sense, or from topological arguments at least. Yeah. We know that the prime manifold decomposition exists in all dimensions except for 4. 4 dimensions is not known. And so we are most interested in the low dimensions 2 and 3, but perhaps also 5 and higher. Yeah. So now that this manifold decomposition exists, can we do something by, in a data-driven way to get to it? And notice first that the harmonic eigenvectors, supposing that we have these harmonic eigenvectors to high precision and correctly, because they are parameterizing a space, because they correspond all to the eigenvalue 0, any rotation of the harmonic eigenvectors is also a rotation of the harmonic eigenvectors. Yes, and so we want to prove that if we take the basis, the harmonic eigenvectors of the component manifold, and put them together, there exists a rotation of these y's that actually is close to this decomposition. Yeah, and this is what the orthogonal cone structure refers to. Here we show what's happened in spectral clustering. If we have two very weakly connected components, then the spectrum of the Laplacian, of the zeroth Laplacian, decomposes into not just two disconnected sets, but also two orthogonal. These sets are also orthogonal. Yes, and this is what we are going to look for in the decomposition of the first order Laplacian. In terms of algorithmics, we are going to treat this as a, so if we are going to prove something about it, we are going to prove it by means of matrix perturbation theory. So we are going to assume that up to a rotation, these vectors are a small perturbation of a completely disconnected set of manifolds before the connected sum. Yeah. And in practice, we are going to find this rotation by independent component analysis. Yeah. So the theoretical contribution in proving that this is this connection, the connected sum produces a small perturbation to the eigenvectors. So the theoretical contributions are the fact that we can do this under certain conditions, and then we do it by algorithms that are not themselves exactly proved to have guarantees, but we prove that the solution exists in the space in which we look for it. Let me give you a feeling of what we are trying to do. So suppose we estimated the first order Laplacian, and we get these eigenvectors y, denoted y, yes? And these are the first row of the table. Now, if we plot the edges, so there are 4 eigenvectors because this is gluing of 2 tori. Yeah. If we plot eigenvectors, the pairs of edges in this space, which is called the homology embedding, we get these red figures. However, if we find the correct rotation 3, then we see that each of these coordinates is supported on only one component. So this coordinate and this coordinate are supported on the left torus, and these other 2 coordinates are orthogonal and supported on the right torus. And in this plot, this is shown by basically having orthogonal and independent components. There is always going to be something at 0, and ask me if you want to know why that is. So this is what we want to obtain. We want to obtain sets of eigenfunctions that are localized on one of the prime manifolds of our composite manifold. And I'm going to skip through the assumptions. The assumptions only say that the sampling, the topology obtained from samples is the same as the topology of the original manifold, and that the sampling in the gluing region is low density. Yeah, so the contribution to the weight matrices is small from the parts that are changed. Okay. And under these conditions, we have the following result. If these, so these epsilons bound the local changes. Yeah, we can bound the error in the Laplacian up and down Laplacian at any Laplacian k. Yeah, so this is not just for the one Laplacian. By these errors, by individual errors. And then by using the standard matrix perturbation theory result, these errors divided by the eigengaps, by the principal eigengap of the matrix, give us the perturbation between the current eigenvectors and the eigenvectors of the decomposed manifold. Yeah. And if this is small, it means that there is a good approximation in the Laplacian eigenvectors of the decomposition that we don't know, but we are looking for. And this assumption involves the fact that the topology is not changed. This assumption of sparse connectivity bounds the error of the denominators in the individual Laplacians. And I want to also highlight that basically these are, there is a change in the support of these 2 vector fields because we remove some nodes and add other nodes and the edges. That's actually not very significant. Okay, so what can we do? Practically, what we do is we compute the Laplacian, we do the eigen decomposition and get the null space, and then use independent component analysis. And this shows this is a schematic on a very simple manifold, but like a real manifold of what's happening. The original eigen decomposition gives us these 2 directions, which are not localized. And by rotation, we obtain these other 2 directions, which are aligned with the two loops in this simple manifold. And now from this, we actually develop a spectral homologous loop detection. I want to skip, I want to go fast through it, but basically, since each of these presumably represents a loop, if we pick the most representative, which are like the most outlying edges in this embedding, they will correspond to edges that are always near the smallest possible loop in this harmonic eigenflow. And so by a form of Dijkstra algorithm, we obtain small loops in various situations. And this is an RNA single cell experiment, which gives us a non-trivial topology. This is a sculpture. This is the ocean buoy set in a place where there are islands. So therefore, we need to find loops. And this is actually a vision data set. And here we use a different complex. We use the cubic complex. So our theorems also are useful for the cubic complex. What is below shows basically what happens if we don't do the independent component analysis, if we use the original vectors. Many of the loops are missed. Okay, with this I have arrived to the end of the talk. And I want to summarize the fact that in the first part of the talk, we were interested in interpretation of the learned manifold through sciences, for the sciences. And in the last part of the talk, we're interested in actually bringing more of the mathematics, or of the beauty of mathematics, in the context of learning from point clouds. Yes, so that even though we may not know our manifold and vector fields analytically, we can do as much as possible with them in a data-driven fashion without actually using their analytic forms. That is actually the main goal of what I tried to do here. And with this, I thank you, and I also want to thank my collaborators, both in statistics and in chemical engineering everywhere.
All right, let's thank the speaker.